in those lectures to come at some point rather quickly to the dynamics of spin glasses and not only statics. But I didn't plan to spend so much time on the statics, but it's a little longer than what I thought. So now we're going to wrap up what we've started, and with the notion of real probability cascade and Ghirlanda Guerra and all this, we will prove or at least sketch the proof of the Parity formula, right? Which is, so you'll see, up to now what we've introduced is in some sense is something about the structure of the Gibbs measure, and we will use this information to prove something about the free energy, which is the Parity formula. So since you probably have forgotten the Parity formula already, so let me remind it to you. And so we want to prove the following. We again have, so remember we have our mixed spin Hamiltonian. So that's our Hamiltonian. On the, from p equal 1 to infinity, on the cube, of course, and the beta p's are decaying fast enough for this to make sense. Then, and so remember that we decided that to note that, so the covariance of this Gaussian vector is simple. It's just n times a certain function nu of the overlap, where nu of r is just the sum of beta p squared r to the p. And of course, the overlap is just normalized in a scalar product, okay, which is between -1 and 1. So that's our model. And then we consider the partition function, which is sum of exponential h of sigma, hn of sigma, for sigma n being this cube here. So that's the partition function. Maybe, I could put here a negative beta to temperature, but it makes no difference, right? Because putting a beta here or changing those beta p's make no difference. So it's the same model. And the negative just, of course, makes no difference because the distribution of these guys, if you remember, is of course invariant by changing the sign of sigma, except for plus or minus 1, depending on the parity of p. So that's no big deal. And so we want to understand, and so the free energy is just, we want to understand this, the mean of log of Zn. And so, I'm sorry, maybe I should write the Parity formula, which is, of course, due to Parisi initially and proven by Guerra, Talagrand, and recently improved by Penchenko, is just the following: the limit of 1 over n of expectation of 1 over n log Zn of the mean of the free energy is the infimum of this function that I call Parisi of zeta over, or I call it rho maybe, over zeta. And this zeta is a distribution function on the interval 0, 1. And in fact, this infimum, you can either define it for all possible distribution functions on 0, 1 or simply for the discrete ones. So here, if zeta is a discrete thing, so let's say we have r numbers like this, and so again, the q's are the location of the atoms and the zetas are the masses of the atoms. So this defined, if you want, a probability distribution on the 0, 1, which is such that qk, mass of this atom is simply what I call zeta k minus zeta k minus 1. Okay, so this defines a probability distribution in the interval 0, 1. For such a thing, then the Parisi, I define Parisi, the Parisi function of this zeta, which of course also depends on the family of beta p's or on the function nu, which is the model of this. This is defined in this strange way. it is expectation of x0 minus 1/2 of sum of zeta p's from sum of a p, 0 to r minus 1, of theta of qp plus 1 minus theta of q, p to the power 1/2. That's the Parisi functional, where the function theta, which I could keep here, theta of r is just, I keep forgetting that. What is it? It's, I think it's r nu prime of, okay. All right, I'll find this. Let me write it as, it's sum of p minus 1 of beta p square r to the p. That's the best way to write it. Okay, so it's also, yeah, it's r nu prime of r minus nu of r. Okay, if nu is this, nu prime is p r p minus 1. So if you multiply by r, you get this p here, and then you subtract this one. All right, so that's the function zeta. So this, the function theta. So this is the Parity functional, and there is one thing that I haven't defined here. So this is easy. It's just this sum on zetas. But this is the important term. So how do you define x0? You first start by a function xr, again backwards, remember. And this xr is simply log of 2ch of eta 0 nu prime of 0 to the 1/2 plus sum of eta p's nu prime of qp plus 1 minus qp nu prime of qp to the 1/2, sum of the p's, from 1 to r. And the eta p's here are IID and 0, 1. So you define this final random variable, log of 2ch, I should write this better. And then you integrate backwards. Then you define XL to be the expectation 1 over zeta L, expectation of log, log of expectation under L of exponential zeta L XL plus 1. And this integration here is integration with respect to eta L plus 1. So we described this 2 or 3 times ago. You take this variable, which depends on all those random variables, eta p's, and gradually you integrate first the last variable, then the second to last, etc. And this is what you call the XL. And you end up with an x0. And this is the expectation of this x0. All right? Good. And something must be wrong here. Yes. No, something is not wrong. An important thing to notice is the following. Here we have nu prime of 0. Nu prime? Yeah, nu prime of 0 to the 1/2. So when beta 1 is 0, right, then this nu prime of 0 is 0. So when you don't have the p equal 1 term, this term is not there. So when you integrate all the random variables, all the eta p's, this x0 becomes deterministic. So then you don't even need the expectation. When you have this first term, then the x0 stays Gaussian. X0 will be simply a function of eta 0, a complicated function of eta 0. Right? So it's still random. All right, so that's the Parisi formula, which looks strange and complicated, but that's what we want to prove now. So how is that linked in any way with what we've done on the Ruel probability cascade, right? So remember what we did? I introduced this, then we went into the study of the Dovbich-Sudakov theorem and the structure of the asymptotic Gibbs measure, the random overlap structures and all this. The role of the Ghirlanda Guerra, which helped you prove everything you want on these objects. Then, yesterday I introduced the real probability cascade and showed that there we had a natural set of Gibbs measures which satisfied the Ghirlanda Guerra thing, but it has nothing to do with this a priori. So here's the link. So let me remind the notation that we had yesterday of, so for any alpha in my set A, which was this infinitary trees, then I would define, I had this weights V alpha and the vectors H alpha, which were unit vectors in the Hilbert space. And these were defined yesterday, right? So let me remind you, this is a tree, the tree of, and then in fact here, I'm sorry, I don't even need to define this on the tree. Alpha is in n to the r. Right? So these are the leaves of the tree that I defined yesterday. And for any such thing, we define a weight. And remember how. You have this tree, so an alpha, let's an example. Let's take alpha equals 7,352. Right? That's one element here with r equal 4. So at this level here, you choose. So what you do is at this level here, you choose a Poisson-Dirichlet process with exponent given by what we call zeta 0 over there, or zeta 1 rather. Then, so here you choose a Poisson-Dirichlet with zeta 1. Here you choose completely independently a Poisson-Dirichlet with zeta 2, etc. Okay? And the weight, V alpha, is just the product of those weights you had here. So I'm sorry, I did something wrong. You choose a Poisson-Dirichlet of zeta 1 at level 0. So I should do it like this. I should do the picture. You have the root here, then you have 1, 2, 3. So here, 7. 1, 2, 3, 4, 5, 6, 7. So at this level, you choose, remember, a Poisson-Dirichlet with the parameter zeta 0. Yeah, because I shifted my numbers here. And so this is, if you want, at level, this is 7 here. You take the 7th value of a Poisson-Dirichlet given by this parameter. Here at this level, you sample a Poisson-Dirichlet of parameter zeta 1. Right? And so now you have 1, 2, 3. You take here the third atom. The weight here is given by the third atom of this Poisson-Dirichlet. And then you have here 1, 2, 3, 4, 5. Here you have drawn a Poisson-Dirichlet of parameter zeta 2. And you take the fifth atom of this, the fifth weight of that. And then here you have 2. Here you draw a Poisson-Dirichlet of parameters zeta 3, and you take the second atom of it. All right? And here you have your alpha. And remember, this is the path, what I call P of alpha. And the weight here is just the product of this by this, by this, by this. Okay? That's my weight. And remember, I also define so the weights are defined independently of the Q's. You just need the zetas. And then once you know the Q's, you define those vectors on the separable Hilbert space in terms of the Q's, and I did that yesterday. All right, so we have this. Now, once we have this, how is that related to the Parity functional? So I start with a zeta like this. From this zeta, I define those objects, right? So if you want a Gibbs measure on the Hilbert space, which is there. So these are the weights of these guys. And then now you do the following. You show that this is the important lemma. You look at the Parity Functional of this zeta. It is in fact expectation of log sum over the alpha in this leaves to the r of the v alpha that I just recalled times 2 cosine hyperbolic of g nu prime of h alpha. I will say what that is. Minus expectation of log of sum over v alpha exponential of g theta of h alpha, where the g's, where, for any function, for any psi, function psi, you define g psi of h alpha are, so these are Gaussian vectors indexed by the alphas here on this thing, and which are simply eta 0 psi 0 of 1/2 plus sum of eta beta psi of q beta minus psi of q beta minus 1 to the 1/2. And you take that for the beta in the path of alpha. The thing I just erased, the path that goes down from the root to alpha. So for any function psi, and the etas here are IID and 0, 1. So this is very reminiscent. Look, it's exactly like what we have here. Okay? So this is built, so for any function psi, you can construct this object on the tree. Here we are still in the world of the real probability cascades. Nothing to do with Parity Formula a priori. This is built so that the covariance, so these are, of course, now Gaussian variables indexed by the leaves, right? But the covariance is very nice. The covariance of this is, of course, h beta is simply the function psi of the inner product of h alpha and h beta. Okay? Right? But you have to remember what was the definition of the h alpha and h beta. If you take psi of x equal x, then this here, this disappears. Psi of 0 is 0. And this here is exactly the definition of h alpha, right? So you get this. All right, so of what we call G alpha, I'm sorry, before. So that's the thing. And here you choose, in this formula, you choose psi to be nu prime, and in this formula, you choose psi to be theta. All right, so let's look at this. This formula is very interesting. This is the link between real cascades and the Parisi formula. It's still not a link with spin glasses. I mean, you still have to prove the limit theorem. But at least what's happening in what is in the right-hand side of Parisi formula, this thing here, has a representation in terms of real probability cascades. So this is a very important formula. This is this function, whatever it is, which will be giving the limit of the free energy. And this thing on this side is defined in terms of the real cascades. There you have the real cascades, right? So you have the V's here, so the zetas are encoding those V alphas, and the Q's, the location of the atoms, are encoding those H alphas. And they are here, or those G of H alpha, and they are here, right? So this formula, a priori, is just an algebra formula, which is purely inside the real probability cascade theory. It says, let's imagine you want to compute this crazy function on a real cascade. You can, and you find that it's this thing over there. So I won't give the proof of that. This is a direct consequence of what I said yesterday about all these. I gave you properties of invariance and all that, and computations. So this is easy. This is algebra, if you want. All right? But this will be the important thing. So again, the interesting part is that in this approach, we see this limiting object as being linked to the real probability cascades. We are not trying to put the real cascades in the finite n object directly. Okay? Right, so now that we have this, we can go on. And so the next step, so now we're trying to prove the real the Parisi formula. So remember what we've learned. We want to say something like that. Take the Gibbs measure, which I call Gn, for this guy, right? Take the Gibbs measure of this. Define the overlap matrix. Prove that this overlap matrix satisfies the Ghirlanda-Guerra property, at least approximately, for finite n. It doesn't have to be exact for finite n. So that when you go to the limit, it becomes an exact Ghirlanda-Guerra. Then you say, so every limit point for the distribution of the overlap will have to be given by a Gibbs measure. We explain all that. And satisfying Ghirlanda-Guerra, this thing will be determined entirely by what we call the functional order parameter, that is the distribution of one overlap. Okay? And now, for any such overlap, one distribution of one overlap, functional order parameter, we know that the distribution of the overlap matrix, once you know the distribution of one element, and once you know it satisfies Ghirlanda-Guerra, has to be the one that you obtain from the real probability cascade. Right? So the only thing here is that in the Parisi formula, you don't know what the functional order parameter should be. So what you want to do is to compare your system, your finite n system, with something that has to do with a real cascade for a given functional order parameter. And then prove that you can optimize on that. Okay? So for this strategy to work, you need first to prove a Ghirlanda-Guerra thing, approximate identity. Second, of course, you will need to understand some way to interpolate between the real model here and the one with a given functional order parameter for a real probability cascade. And that's the Guerra approximation thing. Okay, so let's start with the first step is proving Ghirlanda-Guerra, or some approximate version of it. So the thing is that this is hard. You cannot really prove Ghirlanda-Guerra for the given Hamiltonian we have here, even really approximately. In order to do that, you have to perturb a little bit the Hamiltonian. So what is done, it's you introduce a tiny perturbation of the Hamiltonian, which will be tiny enough to not change the free energy, but which will be strong enough to make the Ghirlanda-Guerra identity approximately true. So that's a little tricky. Okay, so that's what is done here. So let's introduce this perturbation of the Hamiltonian. The Hamiltonian here, and you introduce the following thing. Let me call Gp of sigma to be the sum 1 over n to the p over 2, sum of gy I1 IP, sigma I1, sigma IP. So this looks exactly like the HNP, except for this power. The HNP has the power p minus 1 over 2 here. So this is much smaller. This is 1 over square root of n smaller. right? It's a small perturbation. And these G, I1, IP are, as usual, IAD and 0, 1, and are also independent of the couplings that define the HNP. Okay? So this is a small perturbation, exactly the same order than that. And now you define G of sigma to be the sum of 2 to the minus p, sum over p, 2 to the minus p, some coefficients xp, gp of sigma. This will be our perturbation. You want to perturb in every order. And these xp's will be numbers, real numbers, deterministic here if you want for the moment, which will be, say, between 0 and 3. Not very important, but you want something bounded here. All right, so this G, as I said, is much smaller than the H, because you have a factor 1 over square root of n. So this is a small perturbation. And now we will consider a perturbated H perturbed, which will be our H over there, plus, say, S G. And S will be a small parameter. Okay? So you change a little bit the Hamiltonian, so you change a little bit the Gibbs measure, but you say, okay, that won't change too much. And so I mean, it's very easy to prove by just Jensen's inequality that if you look at the free energy, so 1 over n log of expectation of the sum or sigma of exponential h of sigma plus s g of sigma. So you look at the free energy when you add the perturbation, that this is essentially the same order of magnitude. It's in fact bounded above by the same thing when s equals 0. Plus, so it's really not hard, plus it's s squared over 2n, sum of 4 to the minus p x to the p squared. Okay? And you have a lower bound which is of the same order than that, and it's larger than this. So this is elementary. This is Jensen's inequality applied twice. So this tells you that if you choose this thing to be small, s depending on as a function of Sn, such that Sn is a little low of square root of n, so that this goes to 0, then the two free energy will be the same. Right? Then the perturbation doesn't change, does not affect the free energy, the asymptotic of the free energy. So if we want to prove the Parisi formula for this Hamiltonian, we could as well prove it for this perturbed Hamiltonian. And the choice of the xp's are anything now. All right? So that's what we'll do. So we'll perturb the Hamiltonian because it will help, as we'll see. All right, so that's the first thing. The next thing is we need, so S should be small enough so that you don't perturb the free energy. But now S should be large enough so that you have Ghirlanda Guerra. So let's explain this. So let me define and state Ghirlanda Guerra. Let me, for a fixed n, a fixed p, and a fixed function f. F is a function of the overlaps of size up to n for the replica up to n. And you define this to be simply what should be 0 if Ghirlanda Guerra was true. So it's absolute value of expected value of f r 1n plus 1 to the p minus 1 over n mean of f, mean of R12 to the p, minus 1 over n, sum from 2 to n, of mean of f r1 L to the p. Okay, so remember, if Ghirlanda-Guerra were true, this thing would be 0. In fact, for any function of r here. So here this is Ghirlanda-Guerra applied to the function psi of x equals x to the p. This is this p. N is, of course, that we're looking at this size little n by little n. And f is the observable you're looking at. This f is a function of the overlap for LL prime smaller than n. All right? So saying that Ghirlanda-Guerra is exactly true is saying that this thing is 0. So the question is that 0? That's the Ghirlanda-Guerra identity. So we won't prove that it's 0, of course, but we'll prove that it's small. So the theorem is the following. So that's the Ghirlanda-Guerra thing, which, of course, is proven by Panchenko here. So if Sn is such that, so we need over there that Sn is a little o of square root of n. That's in order not to affect the free energy. You will need Sn go to infinity. We will see why. This is, in fact, to have the Talagrand positivity principle. And then we'll need something else. We'll need Sn to be not too small. We want that a certain function nu n of Sn, it's not the same nu, divided by Sn squared should go to 0. And I will say what this function nu n is. If all that, then the limit of this delta is 0. Okay, so what does that mean? Then it's for every p, for every n, so for every p larger than 1, for every n 2, for every f, you have this. Again, this limit is, of course, when capital N goes to infinity. Unfortunately, you don't really have this. You have this in an integrated version. So remember, our perturbation model is, we are integrating, I mean, our Gibbs measure is given by this perturbation. And in the perturbation G, you have these parameters xp. Right? So a priori, you have one model for each x, each choice of xp's. So what this is saying here is that this thing here is when you integrate, this ex means that you integrate with respect to the x's, say, as a uniform distribution on the interval 1, 2, right? Which is an interval inside the 3 here. Okay, so if you average on the x's, then you have this Ghirlanda-Guerra thing. Okay, it seems like a weak statement, and you see now we're really deep in the trenches. It becomes complicated to find your way. But you need something that says we have Ghirlanda-Guerra. Right? So I didn't say what this guy is. So I have to say that. So this nu is a concentration function. So the define phi to be the log of Zn for this perturbation thing. Okay? So it's the log of the sum over sigma of exponential h sigma plus s g sigma. Look, this phi is, of course, a function of x, of the collection x, because you have an x in this g. It's also a function of many other things, but I consider it as a function of x. Then you have a concentration result. Let's assume this. So the soup of the phi minus expectation of phi for every x. Let's assume that you have this. For every x between 0 and 3, and for every p, and call this nu, it's more than a certain nu n of s. Assume this. That defines nu n. So assume that you have this concentration, right? So nu n is defined by this, if you want. It's the soup. When I say soup, it's the soup in x and the soup in p. Right? So that's the nu n. Okay, it looks like it's not easy to work what it is, but in fact, when you start with this mixed p spin model, you can compute the nu n, and we'll see that. So in particular, when you take here in our case, then you can take nu n to be whatever constant, which is 5, n nu of 1 plus s squared to the power 1/2. So this is just concentration inequality for Gaussian random variables. I don't want to get into that. So this is, of course, you have to prove. So in particular, a possible choice of Sn would be n to the power gamma, so with gamma between 1/4 and 1/2. Okay? So all this, I mean, you can forget that. You could simply choose, remember just that. You take Sn, this order of perturbation here, to be strictly n to the gamma, with gamma smaller than 1/2. That we know we need in order to not change the free energy. And larger than 1/4, this is what we need to have the approximate Ghirlanda-Guerra. All right? Good. So let me not go into how you prove Ghirlanda-Guerra, but just let's accept it. So one more thing. And here, okay, this becomes really complicated, but one word. If we had exactly Ghirlanda-Guerra, this is not an exact Ghirlanda-Guerra. This is approximated in the sense that this is not 0 but goes to 0. This is a limit result. And on top of that, I have to average on those x's. If I had an exact Ghirlanda-Guerra, we would know from what I said last week that we have the Talagrand positivity principle, which means that the overlap is supported on the non-negative numbers. Here we have some kind of approximation of the Ghirlanda-Guerra, so we don't have the Talagrand positivity principle. We will have it at the limit, but not at fixed n. So you have to prove some kind of Talagrand positivity principle, and this is done here. So you prove that the probability that the overlap is smaller than negative epsilon is going to 0 in some approximate sense. Okay, that's important because, again, this zeta that you have in a Parisi formula are supposed to be the distribution of the overlap. And I said it's carried by the interval 0, 1. So you don't want the overlap to put mass on negative 1/2. Right? So you have to prove that. So let's assume that we have the Talagrand positivity principle. Then we are now equipped to go for the proof of the Parisi formula. So we start by the proof of the upper bound. And this is due to Francesco Guerra. So Guerra introduced so what we want to prove, of course, is that the lim sup of 1 over n log Zn, our free energy, is smaller than the Parisi of zeta for any zeta. Right? That's what we want to prove. If we can prove that, then of course the lim sup will be smaller than the inf. And then once we prove the lower bound, it will be, in fact, the limit will be equal to the inf, which is what we want to prove. So here, to prove the upper bound, this upper bound by Guerra, you fix a zeta, as we did before, a distribution, and try to prove this. Okay? So what do you have here? Of course, the trick is to try to compare our problem here with this mixed p-spin Hamiltonian to something in which you have naturally a zeta, which of course will be a Ruel probability cascade defined by zeta. Right? And you want to compare the two. So how do you compare the two when these two models have nothing to do one with the other? Right? So you need to be Guerra had to be very, very courageous here to do that. What you do is the following. You introduce an extra parameter, let's call it t, and you create a path of Hamiltonians, right? Depending on t, such that the Hamiltonian at t equals 0 is the one you want, and the Hamiltonian at t equals 1 is the one you know. So at t equals 0, you want your Hamiltonian to be this, mixed p-spin model, and at t equals 1, or maybe the other way around, you want the Hamiltonian to be the one given by a Ruel probability cascade defined by zeta. All right? So this is your path of Hamiltonians. Then you do something else even there. So what you do is you add a little perturbation to this whole path of Hamiltonian on top of what we have here. You add a little perturbation as we did before so that you have Ghirlanda Guerra all along, at least approximately. Okay, so that is already heavy. And then you dream of the following thing. Just imagine now that if you look at the free energy along the path, right? So you have a Hamiltonian for each value t. If by any chance your free energy was monotone, positive or negative, increasing or decreasing, then you could compare the free energy at one end with the free energy at the other end. And at one end, you have the free energy for the Ruel probability cascade, which will be given by this Parity Functional because of the lemma that I gave you before. And on the other hand, you have the thing you are interested in. And so this would give you a bound, which is exactly this bound. Right? But in order for this to work, so this is exactly the strategy. But in order for this to work, in fact, you need to dream that the derivative of your free energy has a sign. Right? And that it's not too much destroyed by adding this extra perturbation we need for Ghirlanda Guerra, but forget that. But even without this perturbation, thinking that there would be a sign, well, this derivative would have a sign is really incredible, and it's true. That's the basis of this whole thing. So here's the proof. Now, once I've said that, it's not too hard to see what the proof is. So you introduce, and then introduce the following family of Hamiltonian. I would call HNT of sigma alpha. So my Hamiltonian now is on a double space, because first, I cannot put this Hamiltonian and the Ruel probability cascade on the same space. So this sigma is in my cube, and alpha is in Rn to the R defined by the zeta. I introduce this Hamiltonian. So I take first square root of t Hn of sigma plus square root of 1 minus t sum of from I equal 1 to n of g psi prime I of H alpha sigma I plus square root of t sum of g theta I of H alpha So this is a Hamiltonian. So remember, these guys I introduced some time ago. Okay? and here I take copies of them. This I means I'm taking IID copies of them. All right, so first let's look at this Hamiltonian. When t equal 1, then, oh, this something must be wrong here. Yeah, I guess I have a square root of 1 minus t here. When t equal 1, this disappears, and then here I have my Hamiltonian, the one I want, right? And it does not depend on alpha. It does depend on sigma. When t equals 0, this disappears. These guys are 1, and I get here exactly the object for which I knew. I gave you the lemma. We know that the free energy defined by these guys is exactly the Parisi functional of zeta. You remember this? I just gave you this lemma today. Unfortunately, I erased it. Right? As a property of the real probability cascade, we know that if you take exponential of this part, then sum over alphas, then take the log, then take the mean, then you get exactly this thing. Okay? So when t equal 1, the free energy of this should be that. When t equals 0, then the free energy is this one. Right? So if you can prove that the free energy, the contrary, I'm sorry. At t equal 1, you have this. At t equals 0, you have that. So if you can prove that the free energy decreases when t increases, then you're done. Right? All right. So that's the idea of Guerra. There are two things in what I'm saying here. First, there's this incredible thing to realize that this Parisi functional here is in fact simply the free energy of this model in the real probability cascade, which has nothing to do with our model. First, you need this computation, which we kind of did last time. And then you need this interpolation result. So what you do is you introduce phi of t, which is the free energy, depending on t. So it's 1 over n, expectation of log of sum over sigma n alpha of the v alpha hn t sigma alpha. Okay, so let's look at this. Again, when phi, if you look at this like that, when phi equals 0, when t equals 0, and so you don't have the hn sigma, we know that this is exactly, this one is exactly the Parisi functional of zeta. This is the content of the lemma I gave before. Now, when t equals 1, then this hnt of sigma alpha does not depend on alpha. Look at the formula. So this thing gets out of the sum, and of course the sum of v alpha is 1. So the sum on alpha disappears, and you just keep the sum on sigma of h of exponential of h of sigma. And so this is Zn. Right? So we know with this phi, we know that phi of 1 is in fact 1 over n expectation of log Zn. And we know that phi of 0, because of the lemma that I gave you before, is just the Parisi functional of zeta, because it's purely a computation on the real probability cascade. So if you could prove that phi prime of t is negative, you would be done. All right, but life is not that easy. In fact, in order to do something, you will need the Ghirlanda-Guerra things. In order to prove that. So the question is phi prime of t negative? That would be really nice. Okay? So it won't be true that phi prime of t is negative. Really. But, okay, this phi depends on n. So maybe you don't need phi prime to n to be negative, but to be smaller than something which might be positive but goes to 0. Right? Because in the end, that's just on the limit that you want to work. And moreover, in fact, you need, in order to prove this type of things, this kind of estimate, you need to have the Ghirlanda-Guerra thing. So in order to have the Ghirlanda-Guerra, you have to add here the perturbation I was talking about before. And you take an Sn here, which will be, as we said, n to the gamma with gamma between a fourth and a half. So that this term does its job, which is enable the Ghirlanda-Guerra inequality identity to be true and does not perturb the free energy. So, what is really proved is the following. So, you prove the following. And so, how is that? How do you compute this phi prime n of t, whatever? You prove that it's bounded by a constant. I mean, all this is work, but at the level of calculus, if you want, high level. Okay. It's a constant time expectation under the Gibbs measure square. The Gibbs measure is the one associated to this perturbed Hamiltonian here, of the overlap smaller than epsilon, plus something which goes to 0 with epsilon. That's the basic remark of Guerra. But then, you know by what I just mentioned, the Talagrand positivity principle, because you have the approximate Ghirlanda-Guerra, you know that this thing here goes to 0. Okay, because it's, the probability that it becomes negative is 0, goes to 0. Okay, so what you can prove then from this is that the lim sup in n of the sup in t of phi prime n of t is smaller than a constant times epsilon. So then you let epsilon go, so you integrate this, and this tells you that, and then you let epsilon go to 0, and so this tells you that the lim sup of phi n of 1 is smaller than the lim sup of phi n of 0, which is essentially the kind of thing you want. But now, of course, this is no longer really true. I mean, this is exactly true. This is true. This is not exactly true. But because this Sn is small enough, we know that this will be true in the limit. So we know that this guy here, so the phi of 1, in fact, will be exactly what we want. Will be the limit sup of 1 over n, expectation of log zn, which is the left-hand side of this upper bound of Guerra. And we have to prove that this will be, in fact, the Parisi functional of zeta. All right, so if we didn't have this perturbation here, when you take phi equals 0, we know it's true. It's a lemma I gave before. So let's just believe that the perturbation doesn't change that when you go to the limit. All right? And so then we have what we want. All right, so that's the proof of the upper bound. And maybe it's a good time to stop, because then I have to do the lower bound, which is harder. So historically, Guerra proved this upper bound, and this kind of unlocked, I mean, Talagrand had been trying to prove this for a long time. As soon as Guerra had the upper bound, Talagrand came in something like 3 months with, or I don't remember, maybe 4 or 5, with the other bound, and then the proof. Because at this point, when we read this, it was not clear that this would be the limit. It could be just one bound, and in fact, it is the limit. And so Talagrand's paper of 2004 or something in Annals of Math is really a tour de force. It's really mathematically extremely impressive, and it gets the right bound, but by some perturbation. I mean, why, I remember I gave a class on this something like 8 years ago, or, okay, you can follow it, but it's really kind of a miracle. And in fact, Talleyrand says so. He says, you know, there was a kind of a lucky element in this. I don't want to get into what it is that allowed this beautiful thing to happen. But now, the proof for the lower bound that we have now, that we understand, I mean, following Panchenko, is really, really nice, and maybe kind of simpler in terms of what we do. So the proof is based on the what is called the Eisenman-Sims star representation. So let me explain what that is. So first, before we go there, Alex was saying you need a lot of faith to believe, you know, what Guerra did here is an act of faith. Right? You have this Hamiltonian, you perturb it by this, which comes from a cascade. You add you had a little perturbation that is just, you know, just right, and then you get this derivative to have essentially the right sign. You need a lot of faith. I want to insist on the fact that you need even more. I mean, it's really a lot of faith. There's an element in it which is natural, which is the face here was face in Parisi. I mean, Guerra believed that this, if you believe in what Parisi says, then in the Parisi replica symmetry breaking scheme, then something like that seems natural. It was not doable before you had the Ruel probability cascade, which defined really these objects properly, and also showed that this formula that we had for the Parity function was linked to the Ruel probability cascade, that it could be, in fact, in some sense, instead of writing this, instead of writing the Parity formula by saying it's the infimum of this Parity function, you could write, of course, a terrible formula, which would be it's the infimum of the free energy for the Ruel probability cascade associated with zeta. Right? So this thing is, in fact, just comparing this Hamiltonian with the free energy we're interested in with free energies defined by these probability cascades, and so on. So you needed the real probability cascade, some understanding of it. Then you needed to have faith. But then what's really important here is this says this perturbation here, which gives a definite sign to the derivative. You have one per zeta, right? So this is so look at this. This, of course, here, this psi prime and this theta are natural. They depend on the model. They are defined, they come with the h, with the function nu. So these are natural. But the g of h alpha, which depend on the v alpha and h alpha, their distribution depend on zeta. They are defined by zeta. So, and what we're saying that for every zeta, when you do this perturbation, at this point in the space of models, if you want, for every zeta, the perturbation is such that the derivative has a sign. That's already very, very strong. It says, if you take a p-spin, mixed p-spin Hamiltonian, perturb it in some sense in the direction of real probability cascades, any perturbation in the direction of real probability cascades, then the free energy increases. That's one thing. But it's even stronger than that, because it doesn't say simply that the derivative at this is not the same statement as saying that the derivative at 1 is negative. Right? It's not saying that if you move a little bit away, this is not simply by saying when t is close to 1, this derivative is negative. It's not if you move a little bit away from this hn that you find something less. It's all along the path. The idea that you could do an interpolation from one model all along the path to the other model for all t between 0 and 1, this is, you know, more. All right, so that's for the upper bound. Now let's go to the lower bound and the Eisenman-Sims star scheme. So now we want to prove the lower bound. So the lower bound is due to Talleyrand, and in the version I'm presenting here, this has been improved by Panchenko. So now you want to prove this. But of course, you don't want to prove this for 1 zeta. The lower bound, you want to prove that this is the inf in zeta. And of course, this is the limit inf. Okay. All right, so how do you do that? So this becomes really a little more intricate. So let me introduce the Eisenman Sims star. Maybe there's only one M here. Representation. So this Eisenman Sims star representation is something like an equivalent of what the physicists call the cavity method. So, in words, what is the cavity method for physicists? You look at the system with n spins, and then you add one more spin. Okay? Or equivalently, you look at the system with n plus one spin, and you isolate one spin, and you look at it differently from the others, which means you create a little cavity inside your n plus one system, a little hole where you look at one spin. And you look at how all the other n spins affect this one spin. You look at all the magnetic fields, if you want, created by the magnetic field created by all the other n spin on this little cavity. That's the idea. So in mathematical words, it means you do a recursion, an induction on n. And you try to compare the model at rank n plus 1 with n plus 1 spins to the model with n spins. Okay, so let's do that here. So what they do, so again, we have our Fn, which is our free energy, log of Zn. And so our Zn, remember here, is the sum over sigma of exponential h of sigma plus our little perturbation, which is always there to, and this Sn is like n to the 1, gamma with gamma between 1/4 and 1/2. So this perturbation here is there to ensure the Ghirlanda Guerra things, and thus the Talagrand positivity principle. And so now, here's the cavity method. You look at An, which is the expectation of log of Zn. Oh, I need an expectation here, of course. So you look at this expectation, and you subtract, or Zn plus 1, I'm sorry, and you subtract the expectation of log of Zn. So you look at this thing at step n plus 1 minus the step n. All right, so obviously, of course, your Fn is simply the average. You have the 1 over n that we had here, and then you just do the sum of this telescopic sum. So the sum of the Aj from j equals 0 to n minus 1, if I'm not mistaken. Yes? Right, so that's no big deal. So if you knew that the Aj converged to something, then, of course, by Cesaro mean, this Fn would converge to the same thing. Right? So you reduce the problem of having the limit of this to having the limit of that. Up to now, nothing hard. But proving that this has a limit is hard. Or that's not the if we could prove directly that there is a limit, we wouldn't need the lower bound of Talagrand and the upper bound of Guerra. We would directly have a limit. So here we just need a lower bound. So what will be true is that from this, of course, is that the lim inf, because that's what we're interested in, the lim inf of Fn, which is this. Okay? And again, I remind you that this thing, because gamma is smaller than 1/2, will not affect the limit of Fn. Okay? That's what we said. So it's as if it was not there. So the limit of Fn is larger than the lim inf of An. Okay? Obviously. So in order to prove the lower bound in the Parisi formula, we need to prove the limit of Fn, the limit inf of An, is it larger than the inf of the Parisi functions. That's what we need. All right? So now we are taking this guy and we try to work on that in order to get this lower bound. And now this AN has a very interesting, so that's the Eisenman-Sims star representation. It gives a nice formula for AN. It says that AN is the expectation of the log of 2 hyperbolic cosine of Zn of sigma minus expectation of the log of e to the yn of sigma plus a little error, little o of 1. Okay, so I didn't say what yn and zn are, but they play the same role as what we had before, what I call g of psi prime and g of nu. I mean, g of nu prime and g of theta, I'm sorry. So what is this, in fact? So the zn's are, the zn of sigmas are Gaussian, and the yns are independent. I mean, y is independent of the Gaussian random variable, and such that centered, such that the expectation, the covariance, is given by this. Zn of sigma prime is nu prime of the overlap and the expectation of yn, the covariance of yn, is given by theta of the overlap. Okay? So this exactly plays the role of what I called before the g nu prime and the g theta. Yeah. Except before they were indexed, they were on the Ruel cascade. Here they're on the cube. So it's a Gaussian process whose covariance also depends only on the distance or the overlap. And the function here is nu prime, or the function is theta. Okay? So this is a very interesting representation, because now we have something very explicit in terms of this thing. So this error here will be, for the moment, let's say not much about it, but it's small. There is an element here which I have to change. It's not, in fact, this, it's that. There's a prime. And prime means the following. Prime means that I take I look at the perturba Hamiltonian. So H prime, it's really a tiny perturbation, but it plays a little role. So H prime of NP sigma is 1 over n plus 1 p over 2, p minus 1 over 2, the sum of gi1 ip, sigma I1, sigma ip. So if you look at it, it's really the same as HNP of sigma, except I change the n by n plus 1 here. Okay, because we have that's minor inconvenience. And that's what this prime means. Right? Remember, this meant averaging for the Gibbs measure. So of course now you have the Gibbs measure. Let me call it gn prime of sigma, which will be simply the exponential of my hn prime of sigma, which will be the sum of these guys, plus my little perturbation, Sn of gn of sigma normalized. Okay, so this prime simply means this. Okay, and so this prime here means this correction. All right, so what we know so now that let's assume, so that has to be done. This is not that easy, because you have to, to prove that you have this little of 1 here. You're not working on a real cascade here. You're not working on a tree. You're really working directly on the cube. So this is a little harder, but let's take it for granted. And so now what you know is that the G prime n satisfy the approximate Ghirlanda-Guerra identities that I gave before. That's the role of the G, because of the Sn. Because we have this Sn, we know that we have the approximate identity. Okay? I did it for the Gn, but G prime n is the same thing. So now, here comes something which is really a little painful. So, all right, so let me explain. In the perturbation here, you may have forgotten that, and now I'm getting too deep in the trenches. This Gn had an element of choice, some parameters which were the x's, right? Remember that our approximate Ghirlanda-Guerra identities involved an expectation on these x's. Right? Our approximate Ghirlanda-Guerra where you had to take a mean on the x's. So here what you want to prove, so a priori this an depends, it's an an of my collection x of parameters, right? Because this perturbation here depends on x, if you want, right? All right, and so what you want to prove is it is possible, so I could explain that, but maybe you don't want to get that much into the weeds. It is possible to choose non-random xn's which is of course a family of xnp's, such that you have the Ghirlanda-Guerra identities for these x, not averaging on x. And on top of that, the limit inf of our Fn, which of course depend on this x, is larger than the limit inf of the an of these xn. And which of course, where the an of the xn's are by the Eisenman-Sims star representation equal to this expectation of log of 2ch hyperbolic cosine of the Zn prime minus expectation of log of exponential of the Yn prime. And remember that the xn's are hidden in this because they are hidden in the Gn through the little gn. All right? And now the question is, can you prove that the limit inf of this an, now when you take this an, you want to prove that this limit inf is, so we have this an, and remember that for any zeta, we had this Parity Functional of zeta, which is the thing we want to compare this to, was the expectation of log, something very similar to that, expectation of log of 2 hyperbolic cosine of g of nu prime of sigma minus expectation of log of exponential, I need exponential of, what was it, g theta of sigma. That was, why did I write like this? All right, so the question is, these two things look, I'm sorry, I forgot the, here and here. These two things look very similar, but this one is really on the cube. This one is on the, and so the question is, how do you prove anything like this? So now I will do with, so you want to prove that the limit, so Okay, what is the strategy? Now I have to rewind everything. So fasten your seatbelt and take back everything I've said up to now. But I've already mentioned that many times, so now it should sink in. Oh, plus, I mean plus Ghirlanda, Guerra with these xn's. So, do the following. Define your Gibbs measure, as we have here, this G prime n. From the Gibbs measure, look at the distribution of the overlap matrix, the infinite overlap matrix of replica. Now, say, as we've said many times, this is in a compact space, so it has limit points. So consider now a sequence nk such that the distribution of the overlap matrix of replicas converges. Okay, so we can do that. You have this overlap matrix, it's in a compact space, there's a subsequence which converges to something. Then the limit point, as we've seen, we said that three lectures ago, will satisfy, I mean, if you use the Dov-Bish-Studakov lemma, will be defined by a Gibbs, to the limit point is associated a certain Gibbs measure on a sphere or on a unit ball initially of a certain separable Hilbert space. Right? That's a random measure, the Rost, if you want, the random measure on a unit ball of a certain separable Hilbert space. Now, activate Ghirlanda Guerra. If you use Ghirlanda Guerra, because we know we have it approximately for this fixed collection of x, you have it for the limit, for any limit. So from this, you get everything you want. You get the Talagrand positivity principle for the limit, which means that the functional order parameter charges only the positive numbers. You need, and you prove also the fact that it's carried, I mean, it's supported by a sphere. And you remember that the sphere is of radius the maximal support by a sphere and not by the unit ball. And the distribution is uniquely characterized by a certain zeta, which is the distribution of one element of the matrix of R12. Right? And on top of that, and also we know that it's ultrametric. All that comes with Ghirlanda Guerra. So now to any limit point, it associated one zeta, which characterizes uniquely this limit point. All right? So now you want to prove that, in fact, this limit inf of the an of xn, right, here, will be larger, that's what we need here, than the Parisi function of any of these zetas. Right? So that's what you... So and then, of course, if it's larger than that, it's larger than the inf of all possible zetas. Okay? And so this part of the proof is, just comparing this and that, proving that this, when you look at this here, you want to prove that the limit of the an of x is larger than this. Right? So you just look at the formula and you work a little bit, and that works. Let me not go more into that. But the trick is there. You want to prove a lower bound. You want to prove that the limit is larger than inf. So the only thing you want to prove is that for some zeta, it's larger than the Parisi function taken on zeta. So what zeta? This zeta. And here you don't even need to prove that for every limit point. You just need to prove it for one limit point. Right? You take one limit point, it gives you one zeta, and you prove that for that zeta, this guy, the limit of this will be larger than this, which is the same formula. Okay? So, I really don't want to go deep. For instance, how do you choose the non-random xn? This is really a little complicated. In order to do that in particular, you need to understand that this error here is uniform in the x's. So it becomes a little technical. But this last argument is really where the whole thing wraps up. Because if you start from the model here, how would you choose a zeta? And the zeta is given by that. It's the limit of this. It's this functional order parameter for one limit point. Okay. Good. So with that, I consider that I have kind of done my best to indicate how you prove this part, the lower bound in the initial paper by Talleyrand is 60 pages long and very, very serious. But it doesn't use this kind of thing. All right. So with this, let me just add one more thing, and then we can move on. With what we've done here, we have the Parisi functional. And as I said, the Parity Formula, we have this structure of the Gibbs measure, of the limit points of the overlap distribution for the Gibbs measure. But that's all. So let me give you one example where we know more. And what we know more, because of course so let me give one example. This is called, Panchenko called that the generic mixed p-spin model. So by generics means the following. Look at you do the following assumption, hypothesis. You assume that the linear span, the vector space generated of the constant, say the function 1, and the function, or maybe of the function xp's, where p equals 0, and p is such that, and all the p's such that beta p is non-zero, right? So you look at the monomials, so the constant, p equals 0, and all the xp's for the p such that beta p is non-zero, right? So for instance, in your mixed spin model is x2, you have a beta 2 and a beta 7, then you just look at the polynomials which are generated by x squared and x7, that's all. Here you do an assumption which is larger than that. You assume that that is dense in the space of continuous functions, equipped with a uniform norm. Okay, so for instance, of course, if you assume that this is satisfied if you assume that for every p, beta p is non-zero, right? If you assume that for every p, beta p is non-zero, then of course, obviously, Weierstrass theorem tells you that the polynomials are dense in the space of continuous functions, right? So if this is non-zero for every p, this assumption is satisfied. I see a silence here. Everybody agrees with me here. But of course, you don't need them to be all non-zero. There's a wide. There is in fact a sufficient condition for this to be satisfied. It's called the what is it? The Munz-Satz theorem, I think, which gives you for what kind of. When do you know that an infinite series of monomials is in fact total in the space of continuous function? And the result is that it's true if sum of 1 over p's, if you look at the family of p where beta p is non-zero, the sum of 1 over p should diverge. Right? So for instance, if this is true for every p, then the sum of 1 over p diverges. Right? But if it's true only, for instance, for every p square, then this hypothesis will not be true. The sum of 1 over p squared converges. Right? So you need to have enough of those monomials. But anyway, so that's the assumption. If you have this assumption, so of course, clearly this assumption is not true for a pure p-spin. Then if you have this assumption, then theorem, so this theorem is now very clean cut. So this one, in some sense, puts together everything in a nice way. Then the distribution, so under the hypothesis, which is over there, the distribution of one overlap, so remember we call that R12. So you take two replicas under the Gibbs measure, and you look at the distribution of this under, of course, the Gibbs measure, so under the mean, under the disorder, and then the Gibbs measure sampled twice, converges to something. Something that we will call zeta star. Okay? So this zeta star will of course be supported in 0, 1. That's not a surprise, because by Ghirlanda Guerra, we know that this limit thing, which will be the functional order parameter, but I mean, that the Talagrand positivity principle is true. So it should be supported in 0, 1. Okay? So if you have this assumption, if you have enough of these terms in my mixed model, then the overlap of two replica converges in distribution. I'm not saying here it has a limit point. I'm saying it converges. And so you call zeta star the limit, and it has to be positively supported. Second, the distribution of the whole covariance matrix, the whole overlap matrix, so you take again an infinite series of replica. So you take Gn to the power infinity. So remember what that is. You take an infinite series of replica, you take the overlap matrix, the distribution of this whole thing now converges. Right? Before I said it has limit points, and the limit points must satisfy Dov-Bish-Sudakov and blah, blah, blah. Of course, this converges to something, to a distribution. Again, we can say the same thing as before, which will be entirely determined by this zeta star, which will be, of course you will have that, and which will be satisfy Ghirlanda Guerra and will satisfy, which will be ultrametric. Right? So this limiting distribution will be, the limit is determined by zeta star, satisfies Ghirlanda Guerra exactly now and not asymptotically, and is ultrametric. Because it satisfies Ghirlanda Guerra. All right? That's a nice limit. And then, so the ROST, if you want, the random overlap structure really converges. And then, moreover, the free energy converges to the Parisi functional of this guy. Which means that in the Parity Formula, the infimum is achieved at zeta star. Okay? And it converges to that. So everything is perfect. That's exactly what we hoped would be true in general. There is one thing, if you're really careful, there is one thing that you see I'm not saying here. What is missing in this statement? inside the logic of everything we've done. We're burning to say something else. At least I am. You would want to say here, this distribution here is the one you would obtain from the real probability cascade defined by zeta star. Right? That's what we've done. If I give you a zeta star, zeta, you construct the probability, the real probability cascade, and you have the overlap structure defined by this. It should be it. It should be the limit. Right? Why I'm not saying that? It's a matter of logic here, not of proof. It's simply because as it is introduced here, I believe, in fact, when I say I am not saying that, of course, I'm taking this in Panchenko's last upcoming book, so he is not saying that. So my interpretation of it is the following. Here I'm not saying that this zeta star is discrete. Right? I imagine that if we say that zeta star is discrete, then this thing would be the one given by, because we have introduced the real probability cascade only for discrete zetas. Right? But it's of course perfectly possible that the zeta star is not discrete. Precisely, you expect it to be not discrete when you have the pure Sherrington-Kirkpatrick case. As soon as you have full replica symmetry breaking, you expect this zeta star to be not discrete, to have a continuous part. So in order to say what I was saying here, you would need to introduce what the real probability cascade would be for a continuous zeta. Right? So it will be a limit of those discrete trees. This can be done. But it's not done up to now I never mentioned these guys. Right? So I cannot really say that. Okay? But if the zeta star was discrete, this would come from the real probability cascade. And what I'm saying now is not proven, so maybe it's obvious, but I imagine that you would have something similar for the continuous cascade in the case that zeta star is continuous. Okay, there's also one thing that we are not saying here. There's another thing which is missing in this statement. Is that here I'm saying, okay, great, this is this, so which means that this is the infimum. Again, if this zeta star is continuous, this is not exactly, this is what we called the extension of the Parisi formula, of the Parity Function. Remember when we defined this for continuous zeta through this nonlinear anti-parabolic heat equation. Okay? I defined what the Parity Functional was for a general measure. Okay? And I showed that when the zeta is discrete, it's the same as the one we've been using now. But there's one thing we're not saying here, is that this zeta star is the unique minimum. It could be that there is another one. Look like it would be strange, one that you don't see in this object, but it's not said here. All right? But anyway, so this is a really nice theorem. And so what I was saying here are kind of small omissions. The really large omissions in this theorem. The next step of the whole theory, what has to be done, it's, of course, understand the structure of this zeta star. Right? It's understand zeta star from the model. From the data which is new, the collection of, or the equivalently, of the beta p's. Right? So in particular, understand, is it true that zeta star is discrete? If it is discrete, how many levels? And if it's not discrete, what is the continuous part? All right? And is there a transition when you change your beta p's? Can you find full replica symmetry, one replica, two replicas? In what regime? So again, I remind you that if you take, and of course it's not covered by this because it's a pure case, but Elizabeth Gardner proved that the physics level of rigor indicated at least that if you take a pure p-spin, which of course is not covered here, then you have a temperature region where you would have replica symmetry, another one where you would have one-step replica symmetry, and then another one where we would have full replica symmetry breaking, which means a case where zeta is Dirac mass at 0, this zeta star, a case where this zeta star has 2 atoms, and a case where zeta star has an absolutely continuous part. So the structure of this zeta star is supposed to be rich. At least in the general case, everything can happen probably. And we don't know that. So that's really the important thing. To find criteria to say this zeta star is a replica symmetry, one step, full. As I told you, I believe that physicists believe that you never find 2 replica symmetry breaking levels in these models. Only 0, 1, or full. All right, so this is really a hard problem. So, and this is we need this to progress. It's as if we have something like the free energy of a, I don't know, Curie Weiss, and you can't solve the variational problem, then you're stuck. So how do you prove this? The proof of that is based on something which is very interesting, a very simple identity, which I think deserves to be given in general. And so you have the following theorem, which is that if you take the Parity functional of a given zeta, you fix a zeta, right? Any zeta. And you look at the Parity functional as a function of the betas now. Remember, the Parity functional is a function, in fact, of 2 things. It's a function of the zeta, through what I call the zeta p's and the q p's, but it's also a function of the model itself, of the nu, or the beta p's, if you want. For a different model, you have a different Parity functional. All right? So now you do the following. You take your Parity function. So if you want, it's a function of the zeta and of the collection of beta p's. Right? And now you differentiate this with respect to one beta p. Let's say beta p0. So you see what you're doing. You're having your Hamiltonian here, and you're changing a little bit one coefficient. You're moving the component, say, on the 17th p spin. Then this can be computed. First, this is differentiable. And second, you can compute the derivative, and it's beta p 0 times 1 minus integral of x to the p 0 d, let's say, whatever, m of x. And this is true for any m. So for any m, which is a limit of the overlap of the distribution of R12 under our usual Gibbs measure. So again, you take the distribution, as here, you take the distribution of the overlap, and it has limit points. You take any limit point, okay, I don't know why I call it m, I should call it zeta. Yeah, it should be the zeta here, zeta. Okay? But that's very nice, because now if you assume that beta p0 is not, let's assume this theorem to be true. If you assume that beta p0 is non-zero, then you find that you can divide by that, and so you find that this oh, no, something's wrong here. What am I saying here? I had M here, and that was for a good reason. So what I want to say is the following. If beta p is non-zero, then this thing is expressed in terms of that, which is independent of m, and so the piece moment of m is fixed. The p-zeroth moment of m is known. So if you have this assumption here that the linear span of the xp's generate everything, for instance, assume that beta p is non-zero for every p, then it tells you that all the moments of this object are fixed. And since this thing is carried by a compact support, then once you know all the moments, then you know the distribution. So that's why it's unique. And once you know it's unique, then the rest will go. All right, so I won't go more into that. This is a computation that I don't want to do. But that explains why you need this guy to be, if this guy is zero, of course, you find nothing. This tells you something like a perturbation, the p-spin component of your Hamiltonian fixes, in some sense, the piece moment of the limiting object here. And so that's why when you have only a pure p-spin, you don't have much, because you fix only the one moment, and that's not enough to fix the whole thing. All right, so I will stop there, and so next time, which is tomorrow, I will drop this. So we have proved the Parity formula, kind of. Again, we can't move much further because we don't know much about the structure of the limiting thing. So tomorrow I will summarize what Tuka, Aufinger, and myself have found in the case of the spherical spin glass. And in the case of spherical spin glass, at least we know one thing, which we didn't prove, but we know in the spherical spin glass that there is, at least for the pure p-spin, at low temperature, the overlap is, it's one replica symmetry breaking. We know that. We know that it's not full. And we expect that when you begin to mix two, then you can see some full replica symmetry breaking appearing. So what we've done with Tuka is study this Hamiltonian on the sphere, its complexity, its shape, if you want. That is, essentially, we've studied this problem at temperature 0. And we've isolated two classes that I will explain, in our opinion, should correspond to the case of one replica symmetry breaking or full replica symmetry breaking. Okay? So this I will explain tomorrow. This draws a completely different method. You don't have to know anything about this. It draws entirely on random matrix theory. So it's a different word, because we will use the fact that we're on the sphere, and so we will use the fact that we have the invariance by the orthogonal group. So we'll see the GOE, the Gaussian orthogonal ensemble, come in, and then we'll draw a lot of interesting answers for the shape of this, maybe of the equivalent of this zeta star when the temperature goes to 0. And a lot of open problems too. Once this is done, then I will go to dynamics, right? And so maybe one remark would be, how can we study dynamics if we don't understand this? Right? This is supposed to describe the bottom of the landscape. The Gibbs measure at low temperature describe the bottom of the landscape. So this is supposed to describe the behavior of dynamics in very long times. So a priori, it's crazy to study dynamics if you don't understand the equilibrium. But here it's not at all crazy, because what we've been able to do for dynamics is very long time, but not so long that you are at close to equilibrium. And what we will see that there is a universal picture that is valid for any of these models. All of them have the same structure in very long time scales and the dynamics, as long as you are not close enough to equilibrium. And this structure is the same as the one that you find in REM, in the random energy model. All right? So of course, the next question, which I cannot talk about because I don't know the results, would be to understand in even longer time scales what happens. And when you go to much longer time scales, then of course you would need the information. When you come close to equilibrium, you would need this information. What is really remarkable is that the behavior of the dynamics of all these models is essentially model independent, even for very long time scales, like exponential in n, as long as you are not really at the mixing time. So before you reach equilibrium in those transient regimes, these models behave all the same. And so this is what we'll prove. And then, of course, we will be blocked going further as long as we don't know the structure of the bottom of the landscape. That is, this zeta star, if you want, when the temperature is low. Right, so that would be maybe for 5 years from now or something like this. But right now, nobody knows how it works. So next week, I will concentrate on dynamics in those long but not too long time scales.